In the last class, we studied the additive property of mutual information and we derived some of the important results. So, these results are depicted here. Mutual information of A and B and C is equal to uncertainty of alphabet A less uncertainty of alphabet A after we have observed B and C. We can also interpret mutual information of A and B and C as uncertainty of alphabet B C less uncertainty of alphabet B C after we have observed alphabet A. The additive property of mutual information is given by this relationship which says that mutual information of A and B C is equal to mutual information of A C plus mutual information of A B given we have observed alphabet C. Now, let us illustrate the additivity property of mutual information by examining the binary symmetric channel. The binary symmetric channel matrix is given as follows: P bar P P P bar, where as usual P bar is equal to 1 minus P. Now, this time we assume that the input symbol either 0 or 1 is repeated, so that the output of the channel consists of two binary symbols B j C k for each input symbol A I. Furthermore, for simplicity we assume that the two inputs A1 and A2 are chosen with equal probabilities. Therefore, we set probability of A1 equal to probability of A2 is equal to half. We have also looked at the relationship of mutual information between two alphabets A and B, which is equal to H of W P plus W bar P bar minus H P. Now, in this expression we substitute omega equal to half, we get I of A B equal to 1 minus H of P. Now, to find mutual information of A semicolon B C, we will use the relationship which we derived in the last class, and that is given by probability of A B C log of probability A B C divided by probability A multiplied by probability B C. The summation is over A, B and C alphabet. Now, the table here gives the necessary probabilities associated for calculation of mutual information. So, A I, B j, C k have been listed. Probability of A I we assume equal to half. Calculation for probability of A I, B j, C k is based on the fact that probability of AI bj ck is equal to probability of bj ck given AI multiplied by probability of AI. If we use this relationship, we get this column as shown here. Similarly, to calculate the probability of bj ck, we use the fact that probability of bj ck is equal to summation of probability bj ck given AI multiplied by probability AI, and this is summed over alphabet A. So, using this relationship, we get the column in this table. So, if we take for this case probability of bj ck given AI, that is 0, and probability bj ck, that is 0 0 given AI equal to 1, we add these two probabilities and we get this result. Similarly, to get this term, probability of 0 1 given 0 and probability of 0 1 given 1, when we add these two terms we get p p bar. Similarly, we get all the terms in this column. Once we have this probabilities, we can calculate the mutual information of A semicolon B C. Now, when we calculate the mutual information, these terms will not contribute to the calculation, because if we divide this half p p bar upon half multiply half p p bar, this will cancel and we will get the ratio equal to 1. So, let us calculate I of A B C equal to probability of A B C log of probability A B C divided by probability of A probability B C summed over A B C. When we substitute the terms from the table, we get the relationship p squared log 2 p squared upon p squared plus p bar squared plus p bar squared log of 2 p bar squared p squared plus p bar squared. So, in this expression only 1, 2, 3, 4 terms come into pictures, whereas the contribution from other terms are 0. Now, this can be simplified on expanding this each of this term, and we will get the result as follows. Plus p bar squared log of p bar squared upon p squared plus p bar squared. Now, this quantity can be simplified as p squared plus p bar squared plus p square plus p bar squared, p squared upon p squared plus p bar squared log of p squared upon p squared plus p bar squared plus p bar squared upon p squared plus p bar squared log of p bar squared upon p squared plus p bar squared. Now, using the relationship that p bar squared upon p squared plus p bar squared is equal to 1 minus p squared upon p squared plus p bar squared, and entropy function which is defined as equal to h omega minus omega log w minus omega bar log omega bar. Using this two relationship, we can show that mutual information of A semicolon B C is equal to p squared plus p bar squared 1 minus h of p squared upon p squared plus p bar squared. Now, the interpretation of this equation is very clear. If we observe the outputs 1 0 or 0 1 from such a channel, its meaning is entirely ambiguous. The two possible inputs will still be equally probable, and we gain no information from our observation. If on the other hand we observe 0 0 or 1 1, we gain information about the input equivalent to that gain by observing a single output from a binary symmetric channel with error probability equal to p squared upon p squared plus p bar squared. Now, we know that information I A B is equal to 1 minus H P if the two inputs are equiprobable. So, using this relationship, the information we get on observing 0 0 or 1 1 is equal to 1 minus h of p squared plus p bar squared. Now, we observe either 0 0 or 1 1 with probability p squared plus p bar squared. Therefore, it implies that the information which I get when I observe 0 0 or 1 1 gets, this term gets multiplied by p squared plus p bar squared. So, this is the information, mutual information of A semicolon B C, which we have derived based on the arguments. Now, we can extend this case of a binary symmetric channel when we have more than a single repetition. For example, if each input produces 3 binary outputs, then we can show that mutual information of A semicolon B C D is equal to p cube plus p bar cube multiplied by 1 minus h of p cube whole over p cube plus p bar cube plus 3 p bar 1 minus h of p. Let us look at the arguments which go in the derivation of this expression. Now, when we observe 0 0 0 or 1 1 1, we gain information about the input equivalent to that gained by observing a single output from a binary symmetric channel with error equivalent to p cube upon p cube plus p bar cube. Therefore, information from such an observation is equivalent to 1 minus h of p cube all over p cube plus p bar cube. Now, we observe either 0 0 0 or 1 1 1 with probability p cube plus p bar cube. Therefore, the information which we gain when we observe 0 0 0 or 1 1 1 will be given by p 3 plus p bar 3 multiplied by this expression. So, this is the one term which we get between the mutual information for the mutual information of A semicolon B C D. Now, when we observe 0 0 1 0 1 0 1 0 0 or 0 1 1 1 0 1 1 1 0, then in this case we gain information about the input equivalent to that gain by observing a single output from a binary symmetric channel with error probability given by 3 p squared p bar upon 3 p bar squared p plus 3 p squared p bar, and this can be simplified as p. Therefore, when we observe either of this quantity, we will get information given by h of 1 minus h of p multiplied by the probability of observing this event. Probability of observing this event is given by 3 p bar squared p plus 3 p squared p bar, and this can be simplified as 3 p p bar multiplied by 1 minus h of p. Therefore, total information which we get between A and B C D is given by p cube plus p bar cube multiplied by 1 minus h of p cube upon p cube plus p bar cube plus 3 p bar 1 minus h of p. We can plot mutual informations versus probability of error for different cases, and if we do this we get this result. In this figure, x axis is depicting p, that is probability of error. On the y axis we have the mutual information, and this is the graph we have for n equal to 0, this is for n equal to 1 and n equal to 2. So, from this graph it is clear that for given probability of error, the mutual information of a binary symmetric channel increases with n repetitions. Now, in our investigation of the additivity of mutual information, we were led to a consideration of the sequence of entropy quantities of the form h of a given b, h of a given b c, and so forth. Now, each member of this sequence is no greater than the preceding member. We also saw that the difference between two successive members could be interpreted as the average information about A provided by a new observation. So, I of A B is equal to H A minus H of A given B. Similarly, I of A C given B is equal to H of A given B minus H of A given B C. IAB is the mutual information of A and B. I A semicolon C given B is the mutual information of A and C after we are given B. Now, both these quantities, however, involve the mutual information of just two alphabets. It is also possible to define the mutual information of more than two alphabets. So, let us define the mutual information of A, B and C alphabet. So, by definition it is given by I semicolon B semicolon C is equal to I A semicolon B minus I A semicolon B given C. Now, our definition of the mutual information of A, B, C implies that this quantity is symmetric in A, B and C. Now, we will try to prove this. So, let us, if this is true, we can write I of A semicolon B semicolon C is equal to I of B semicolon C minus I of B semicolon C given A, or we can also write it as I of C semicolon A minus I of C semicolon A given B. So, to prove the symmetry of this quantity, let us write down the expression for I A semicolon B semicolon C, which is given as I A semicolon B minus I A semicolon B given C. This we can rewrite as summation over the alphabets A B probability of A B log of probability A B divided by probability of A multiplied by probability B. This is the expression for I A semicolon B. Similarly, we can write down the expression for this term, and that is as follows: summation over alphabet A B C probability of A B C log of probability A B given C divided by probability of A given C multiplied by probability of B given C. Now, this can be simplified as follows. We can combine this two term by rewriting probability of A B as probability of A B C, but with the summation over alphabet A B C log of probability A B probability of A given C probability of B given C divided by probability of A multiplied by probability of B multiplied by probability of A B given C. Now, if we multiply the term in the argument of the log, both the numerator and denominator, by probability of C into probability of C, then we can simplify this expression as I of A semicolon B semicolon C equal to summation over alphabets A B C log of probability A B probability A C probability of B C divided by probability A probability B probability C and probability of A B C. Now, by the definition of entropy, we can simplify this expression as entropy of alphabet A plus entropy of alphabet B plus entropy of alphabet C minus the joint entropy of alphabet A B minus joint entropy of alphabet A C minus H of B C plus H of A B C. Now, this expression which we have derived is suggestive of the expression for the mutual information of two alphabets, which is given by IAB is equal to HA plus HB minus H of AB. Now, it is easy to generalize both this expression to more than 3 alphabets, but we will restrain ourselves from doing that because that is not required for our course. Now, it is also important to note that the mutual information of A semicolon B is always non-negative. However, the mutual information of A semicolon B semicolon C can be negative. So, to show this, let us take an example. So, consider the 3 binary alphabets A, B, C. Let AI and BJ be selected as 0 or 1, each with a probability of half and each independently of the other. Finally, we assume that CK is selected as 0 if AI equals BJ and CK is selected as 1 if AI does not equal BJ. So, some of the probabilities of these 3 random variables are given in the table as shown here. So, we have listed all the different combinations of AI, BJ, CK. With each of this combination, we have provided the probabilities of AI, BJ, CK. Probability of this quantity occurring is the probability of getting AI equal to 0 and probability of BJ equal to 0, assuming that each of this is half and they are independent. Probability of 0, 0, 0 is 1/4. Probability of occurrence of 0, 0, 1 will be 0. Similarly, probability of 0, 1, 0 will be 0 and probability of 1, 1, 0 is 1/4 based on the same arguments. Probability of AI given BJ comma CK is indicated in the column here. Now, once we are given BJ and CK, we know with probability 1 what AI we have received. So, if we know that BJ and CK are 0, 0, we know that AI has to be 0 and therefore, this probability of 0 given 0, 0 is equal to 1. Similarly, the probability of 0 given 0, 1 is always 0 because this possibility can never occur. So, based on this argument, we have the listings for the probabilities for other terms. Similarly, we can find out probability of AI BJ given CK. Once CK has been given, if it is 0, then probability of 0, 0 is again decided by the probability of occurrence of AI and that is equal to half. And similarly, probability of 0, 0 given 1 is 0 and probability of AI BJ assuming they are independent are each equal to 1/4 and probability of AI is equal to half. Now, using this table and using the expression which we have derived earlier, we can calculate information of A semicolon B equal to 0 bits, information that is mutual information A semicolon B given C is equal to 1 bit and mutual information A semicolon B semicolon C is equal to I of A semicolon B minus I of A semicolon B given C, and that is equal to minus 1 bit. It is clear why we get such an answer. Since A and B are statistically independent, I of A semicolon B is equal to 0 bits, that is B provides no information about A. Now, if you already know C, however, learning B tells us which A was chosen, and therefore, probably this provides us with 1 bit of information. Now, after having studied mutual information and its property, let us study a very important property of information channel, and that is channel capacity. So, let us consider an information channel with input alphabet A, output alphabet B, with the channel matrix given by P. So, the conditional probabilities, that is probability of Bj given Ai, is specified. Now, in order to calculate the mutual information, which is given by IAB is equal to summation of probability AB log of probability AB divided by probability of A multiplied by probability of B, summation over alphabet AB. In order to calculate this mutual information, it is necessary to know the input symbol probabilities PAI. That means I should know the source model. The mutual information therefore depends not only upon the channel matrix P, but also upon how we use the channel, that is the probability which we choose the channel inputs. Now, it is of some interest to examine the variation of IAB as we change the input probabilities. So, let us reconsider binary symmetric channel with probability of error P. Now, if you have a binary symmetric channel with probability of P, we have derived that I A semicolon B is given by the expression H of W P plus W bar P bar minus H of P, where W is the probability of selecting a 0 at the input and W bar equal to 1 minus W, P bar is equal to 1 minus P. Now, we may plot IAB as a function of W for a fixed P. If we do that, we get this figure. On the x axis, we have probability of a 0 at the input, which is indicated by W, and on the y axis we have mutual information I A semicolon B in bits per minute. Now, from this figure, it is clear that mutual information of a binary symmetric channel varies from 0 to 1 minus H P. The minimum value of 0 is achieved when W is equal to 0 or 1. In these cases, the input is known with probability 1 at the output, even before an input symbol is received. the maximum value of 1 minus HP is achieved when omega is equal to half, that is when both inputs are equally probable. Now, for general information channel, we see that the mutual information can always be made 0 by choosing one of the input symbols with probability 1. Since the mutual information is non-negative, this is an easy answer to the question of what is the minimum value of IAB. The question of the maximum value of IAB for general channel is not so easily answered. The maximum value of IAB as we vary the input symbol probability is called the channel capacity, denoted by C, and it is equal to, by definition, maximum of IA semicolon B over input probability distribution, that is PAI. So, it is also important to know that the capacity of an information channel is a function only of the conditional probabilities defining that channel. It does not depend upon the input probabilities, that is on how we use the channel. Now, from this figure we see that a capacity of a binary symmetric channel with error probability P is equal to 1 minus HP. Now, the calculation of the capacity of an information channel in general is quite involved, but in certain cases, however, the calculation can be simplified. The most important class of channels for which the calculation simplifies is the class of uniform channels. So, let us define what is a uniform channel. Consider a channel defined by the channel matrix P equal to P11, P12 up to P1S, P21, P22 to P2S, PR1, PR2, PRS. As before, Pij is equal to probability of Bj given Ai. Now, this channel is said to be uniform if the terms in every row and every column of the channel matrix consist of an arbitrary permutation of the terms in the first row. We have already dealt with one example of a uniform channel, and that is the binary symmetric channel. Now, the natural generalization of the binary symmetric channel is R array symmetric channel, that is known as RSC. Now, RSC is a uniform channel with R input and R output symbols. The channel matrix of the RSC channel is as shown . So, this matrix is of the size r by r this is a channel matrix of the RSC channel. As usual, p bar is equal to 1 minus p. The overall probability of error for this channel is p, but there are r minus 1 possible incorrect output symbols for each input symbol. Now, we will calculate the capacity of a general uniform channel. The capacity is the maximum of I A semicolon B as we vary the input distribution. I A B is equal to h of B minus h of B given A. This is equal to h of B minus summation over probability of A summed over alphabet A summation over alphabet B probability of B given A log of 1 by probability of B given A. The summation over B in the last term of this equation is a summation for each EI of the terms in the ith row of the channel matrix. For a uniform channel, however, this summation is independent of I, and therefore, we can write I of A semicolon B equal to h of B minus probability of B given A log of 1 by probability of B given A over B. Now, the last term of this equation is independent of the input symbol distribution. So, to find the maximum of the right side of this equation, we need only find the maximum of h b. Since the output alphabet consists of r symbols, we know that h b cannot exceed log r bits. So, h b will equal log r bits if and only if all the output symbols occur with equal probability. Now, in general, it is not true that there exists a distribution over the input symbols such that the output symbols are equiprobable. But for the case of a uniform channel, however, it is easy to check that equiprobable symbols at the input produce equiprobable symbols at the output. Therefore, the maximum value of this equation is, which is the capacity of the uniform channel, is given by C is equal to log of R minus summation over B probability of B given A log of 1 by probability of B given A. Now, using this expression, we can calculate the capacity of the RSC channel as C is equal to log of R plus P bar log P bar plus P log of P upon R minus 1, which can be simplified as log R minus P times log R minus 1 minus h of p. As said earlier, that the calculation of the capacity of an information channel is in general quite involved. In the next class, we will carry out the calculation of capacity for a few more channels, one of the important channel being binary eraser channel. We will look at the properties of binary eraser channel and calculate its capacity.